My name is Marković. I am a PhD student here in Croatia at University of Rijeka, so a different university than Zagreb one, a bit further from here. And I will walk you through my computational method for determining fatigue strength of surface hardened components. So just a bit of beginning, many engineering components like gears are subjected to cyclic loadings or generally really high loadings. And this, of course, results in really high stresses. And then generally what is done is either thermal or mechanical surface hardening or any other heat treatment. It can be done on the whole component. It can be done selectively on this part that we want to alter, but somehow this is what we're mostly dealing with surface hardened steel components. And here I just shown this representative hardness profile that would be taken, for example, from some gear couple at this tooth flank of a gear. So we have this hardness that is basically changing from a higher value to the lower value after surface hardening, of course, to get some mechanical properties, which, depending on the usage, are needed for this purpose. So I took a bit of surface hardening. Yeah, I see now what you went with the PowerPoint getting weird, but I took a bit of state of the art here in finite element analysis of surface hardened components. And what is done basically are these multi-layer models, because as I said, this component is not even on this macro scale, it's not the same because of this hardness that varies, and with hardness other mechanical properties. So what people are doing mostly are these multi-layer models where they sequence the material into much of these layers, and then each layer has assigned a constant value of hardness or constant value of some other mechanical properties depending on the usage. Here they had the constant value. Each layer had its own stress strain curve and strain life curve, and then they computed, I think it was also fatigue life of gears. So then in light with this, we developed this parametric computational model with which then we can calculate the fatigue strength of this component-like specimen, let's say. And since state of the art show that people are doing it with this multi-layer, so sequencing the component, I actually did it as discrete as possible in FEA. So basically on the level of nodes, which means that every node will have its own stress strain curve or strain life curve or similar. So we have a component that really the mechanical properties will vary in each node depending on the discretization. So this is example of this specimen. I did elastoplastic analysis, and because of that, we actually took only 1/4 of the specimen and did 2D analysis, because for elastoplastic analysis it will take really much time to compute for the whole specimen. We also parameterized the model, so we can have multiple notches or central holes or similar. These are the boundary conditions, so these are the symmetry condition basically. And parameterization here show one example with tool radii, but we can have multiple depending on what exactly we want to test. First, what we actually have to have for this is hardness profile. Like I said, from surface we have higher hardness to the core, which has lower hardness, and then I will use these regression equations to correlate hardness to other mechanical properties, similar like this colleague that from Portugal that was here also mentioned. So basically we correlate then hardness to material plasticity, to residual stresses, and at the end to strain life parameters, so we can get actually the number of load reversals to failure. First, about material plasticity, I used the Ramberg-Osgood cyclic parameters, and what was done then, let's say the surface of material would have this specific strain life curve, the central node of material would have this strain life curve, and then all other nodes in between, depending something in between, we can imagine it like this. And for this I used this K prime that is correlated to hardness from which is valid for all materials, also from literature. So just a bit of workflow. We have first meshing, then applying of the hardness on this material, then each node basically has its own hardness value, and then from hardness, each node will at the end have their own cyclic stress strain properties. Then I applied axial loading, so we basically reached then this blue point here. Get some results, like we will need stresses and strains, stress amplitude, and strain amplitude. And from this, we can do the fatigue life approximation or calculation, however. Maybe better to say approximation even. Also, I used for fatigue life calculation Smith-Watson-Topper with mean stress correction. So we can also incorporate the mean stresses. These blue variables I took from the hardness method, the one also mentioned before. And this beginning of the equation, which are basically stress and strain amplitudes and mean stress, were taken then from the FEA, what you saw before. And then, since every node has a specific hardness value, it will also have a specific strain life curve. And basically, we need to solve this upper equation for numerically for 2NF, and then we can obtain the value of each node, so fatigue life at literally every node on this kind of specimen. So if this is then done for some specific specimen geometry, I took this geometry because we will test then experimentally with this one. We can then get 1 point on the strain versus number of reversals to failure on this plot. If we do it for different strains, like this is for total of 5%, if we do a couple of these points, we can actually get a whole strain life curve for this specific specimen geometry. And of course, at the end, get parameters of this curve, and that this would then be parameters of so not from a pure material, but from this component-like specimen, this specific surface hardened material. And just to quickly show you what is planned for, or what is done here and for experimental verification. So we took this material C45E and quenched it to basically get this hardness distribution that I showed you from the beginning. We did this in this sandwich configuration, so the inside of material. So this inside plate we cut into the 2 pieces and measure hardness in 2 directions. And what we wanted to get is in this this direction here to obtain basically constant hardness and to see if we can surface harden it from the left to the right side, which was successfully done. This is shown only for 4 millimeters. So for the rest of the specimen, it was pretty constant, but we have some surface hardening happening here. So then, since we were, I can go back, or I can, sorry. This is then, so this in large is this thing. I took this experimental expression, which is used in literature to obtain the hardness distribution, and calibrated it just for our case from this experimental results. And then we have basically a regression equation that explains how the hardness is dropping in that specimen for our specific material and our specific case. And this is then incorporated into FEA. So it will be even more specific for our case. And now we did this specimen that will be then also quenched in the same way as that sandwich that you saw. So also they should have from left to right droppage of a hardness. They should be surface hardened. And then on them we would perform the cyclic tests. And we will observe two states, one which is shown there, where we have a specimen that is first hardened and then we cut the notch, and the other which we will first cut the notch and then harden the specimen to see what will be the difference, because here the notch is basically cut off. And this is where we stop now. So first up there it says that the FEA model needs to be validated, and the second one it says that we need to include a simulation of quenching or of cooling into the FEA model. So I can also then model this case here, because this is not a linear droppage of hardness. We have a really specific case, and that would then be a complete model for this. Okay, thank you.